So this video discusses about what we call the Coulomb's law. Now, the understanding of the basis of the Coulomb's law has to begin with what we call the Newton's electrostatic law. So according to the Newton's electrostatic law, it states that, let's say we have a charge, I'll call it as a charge 1, and let's say it is a positive charge. And we have another charge, let's say another positive charge, I'll call it as a charge 2. So according to the principle behind the Newton's electrostatic law, there is a force of repulsion between the two charges, and of which the force due to charge 1 on charge 2, it acts towards this direction, given as F21, and the force on charge 1 due to charge 2, it will go towards this direction, and given as F12. But all these forces are the same according to the Newton's third law of motion. And now, what if we have unlike charges? Let's say this is the negative charge, and let's say this is the positive charge. Now, according to the Newton's electrostatic law, it states that there is a force of repulsion between the two charges, and of which the force on charge 1 due to charge 2 will be towards this direction, given as F12, and the force on charge 2 due to charge 1 will be towards this direction, and they're given as F21, and these forces are the same according to the Newton's third law of motion. So what is the Newton's electrostatic law? It states that the like charges repel and the unlike charges attracts. That is according to the Newton's electrostatic law. And Isaac Newton discovered that whenever the charges are being brought together, the force of attraction and the force of repulsion increased. And whenever the further the charges were brought away from each other, the weaker the forces of attraction or the forces of repulsion between the charges. And I even discovered that if the amount of charges, or I should say if the magnitude of the charges increased, and the force of repulsion and attraction also happens to increase as well. But Isaac Newton didn't specify how one can be able to calculate the magnitude of that particular force of attraction and the force of repulsion. Now it was after now the coming in of the Coulomb, who actually came up with a theory on how one can be able to find the magnitude of the force of attraction or the force of repulsion. Hence, that is the essence behind this video, and I want to discuss about the Coulomb's law, how one can be able to find the magnitude of the force of attraction and the repulsive force between the charges that are like or unlike charges. So stay focused. Now, according to the Coulomb's law, let's say this is the charge 1, that should be given as the positive charge. And let's say we have another charge, let's say given as charge 2, and I'll call it as a positive charge as well. And let's say the two charges are separated by some distance, and I'll call it as this is R being given as the separation distance. And of course, there is a force of repulsion between the two charges, and that much we know according to Newton's electrostatic law. But now, according to the Coulomb's law, the force that exists between the two charges, rather this was the work that was initially being done by Isaac Newton, and they discovered that as we are bringing these charges together, the force between them increases. And the further away we are bringing these charges, the force decreases. And as we're increasing the magnitude of the charges, the force happens to increase as well. And likewise is true. Now, according to the Coulomb's law, you have to understand that the force that exists between the two charges is directly proportional to the product of the magnitude of the two charges. So have that in that way. And at the same time, it is inversely proportional to the separation distance and a square. Now for this case, this is the same as having the force directly proportional to the product of the magnitudes of the charges, of course, and divide by, and inverse proportion, that is divided by the separation distance square. So now let's think of introducing a constant and have it out. Now for this case, we have a force being equal to, let's introduce the constant being given as a Ka, the times the magnitude of times the product of the magnitude of the charges. Now this is charge 1, a positive charge, and we have charge 2, a positive charge as well, divided by r square. Now a constant K is said to be the Coulomb electric constant. It just simply says to be the Coulomb's constant. And what is the basis of that Coulomb's constant? So it is given as Ke, and which is given as 1 over 4 pi divided by 1 over 4 pi epsilon naught, where epsilon naught is said to be the permittivity of free space. Mind you, that force of attraction and repulsion exists within some media, and the ability of that force to exist within that particular media, has to be part of being of what you call the permittivity of free space. That is given as 8.8, and that should be 4, and the times, that should be times 10 to the power negative 12, and Coulomb, actually a Coulomb square per Newton meter square. Per Newton meter square. This is the value of the constant, which is permittivity of free space, and it is a dimensional constant. And if we substitute it here, and that corresponds to have the value of the constant being given as 8.99, and that should be times 10 to the power 9 Newton, Newton meter square per Coulomb square. So the Coulomb's constant is also said to be the dimensional constant, a constant that can be measured. It is a measurable it is a measurable constant. So this is what we call the Coulomb's constant, and the value is always fixed, given as that. So this is what we call the Coulomb's law. It states that the force of attraction or the force of repulsion that exists between the two charges is directly proportional to the product of the magnitudes of the two charges, and inversely proportional to the square of the separation distance. That is what you call the Coulomb's law. And the Coulomb's law obeys what we call inverse square law, because always the separation distance has to be squared, so it is said to obey the inverse square law. And also the Coulomb's constant is having some traits, and that seems to be similar to the Newton's law of gravity. And that is that, let's say if we have this is the object of mass m1, and this is the object of, let's say, mass m2, and let's say this is the distance between the two objects, I should say the two masses. And now, according to the Newton's universal law of gravitation force, it states that there is a force of attraction always between the two masses, and let's say this is the distance between the two masses. And how one can be able to calculate that particular force? So the force of gravity, it is given as gravitation constant given as G times mass 1 times mass 2 divided by the separation distance r square. So this one too obeys what we call the inverse square law. But what are the differences between the electrostatic force and the force of gravity according to the Newton's universal law of gravitation force? You should have to understand that always gravitation force is attractive force, while this one can be repulsive or can be repulsive or attraction based on the sign of the charges that are in the system. And while this one is always attractive force. And mostly gravitation force is weaker than the electrostatic force. So those are the typical differences you can have or you can draw from this. And also gravitation force, it deals with the masses, the system of the masses, and while electrostatic force, deals with the charges, as you can see. But all laws deals with obeys inverse square law. So keep that in mind. And always the charges here has to be the magnitudes, and despite whether the charge is positive or negative, but just have to go for its positive value. So take note of that. And the distance has to be in meters, and the charges has to be in Coulomb. So given in whichever they need, contrary from that one, it is your humble duty to actually have it in its basic measure or the unit. Let's appreciate some of the examples associated with the Coulomb's law. Now let's say this is the question: what is the magnitude of a force that is the electrostatic force? So it can be given as this, or just have to say a force, but as it stands here, it means electrostatic force. Now that's what we are looking for. And we have, let's say, charge 1, it is a positive charge, and that is given as 2.5, and we have a micro coulomb. What is micro? Times 10 to the power negative 6 coulomb. And we have a charge 2 that is being given as 1.7. It is also a positive charge as well. We have micro coulomb, 10 to the power negative 6 coulomb. And what is the separation distance? We have 16 centimeter, of which it has to be in meters. What is a cent? Times 10 to the power negative 2 meters. So how should we have this force? That is the Coulomb's law, of which the force is given as actually a Coulomb's constant times the magnitude of the charges and divided by the separation distance square. So try to have that with your calculators, and you have everything. Will be given in newtons. have that. And let's appreciate this question as well. The question says that what is the repulsive electric force between two protons? So now, which means we have the charge 1, which is a proton. We have it as 1.60 times 10 to the power negative 19 coulomb. And we have another charge 2, 1.60 times 10 to the power negative 19 coulomb. Since all these are the protons and they are positive charges, and we have the separation distance, which is given as 2.5, should be millimeter. Of course, it has to be in meters. You convert that to be in the required unit. Now we need to have the force. So what would be that one? You see that the force will be given using the Coulomb's law. Since this and this are the same, it is the same as having Q squared divided by R squared. Then you have everything there. Now let's also consider this question. Two charged dust particles exert a force of 0.005 newtons on each other. What will be the force if they are moved so they are only 1/8 as far back? What will be that? Now we don't know these charges, but we know that we can have a charge 1 and we can have it say charge 2, but we don't know what are these charges. But we have the force. That is given as 0.005. But in this case, the point of interest is on the separation distance between the two. Actually, between the two charges, and with respect to this force. Now for this case, we should have to understand that the force is given as Coulomb's constant, and times the magnitude times the product of the magnitude of the two charges divided by the separation distance. So in this case, we'll be using these charges as the variables whose values are not known. So in this case, we'll have 0.005 is equal, now this is a square by the way, then we'll make actually distance as the subunit formula. And this one will help us now to answer the question that we are taught to. Upon having read, say, the separation distance R, let me have it in this case. We have a KE, now we should have it in this case. So which means we'll have 0. So which means we have it as this. Since we have the force is given as 0.005, so we'll have to cross multiply there. That will be given as 0.005 R square, and which is equal to KE charge 1 times charge 2, and of which R will be given as the square root of, that is a KE Q1 times Q2 divided by 0.005. So this is the separation distance you should have. And now the question says we should find the force. When the separation distance for the two charges is now 1/8 times R. So we should have the force corresponding to the separation distance now being given as 1/8 times R. How should you have that? Principle remains the same. And that is to say, we'll have the force KE times the charge 1, charge 2 divided by the separation distance square. Now what we have now is given us, KE, charge 1, charge 2, divide by, and what is this separation distance? Now that separation distance is given as this, and of which R is given as this. We substitute there, and that will correspond to have it as 1/8 and the times R, which is the square root of, that is KE, and a Q1 Q2 divided by 0.005. Mind you, this square root is for the whole entire thing, in the overall to the power 2. Then you'll be able to simplify and having the force there. So that's how the question tries to ask us about. And let's say we have this question. Two small non-conducting spheres have a total charge of 90 microcoulomb. Now basically we don't know what are these charges, but we know that in this case we may have charge 1, that is we don't know, and charge 2, and that we don't know. But the summation of these charges, it has to be 90 micro, that is 10 to the power -6, in that way. So that is given as the equation 1, because these two variables are known. And when pressed 28.0 centimeter apart, the force exerts on each other is at 12 newtons, and it's repulsive. So which means what you should have to get up is that these charges are actually erect charges, but we don't know whether they are negatives or they are positives. But now we have the force, which is being given as KE, charge 1 times charge 2 divided by the separation distance square. Now the force is given as 12.0, which is equal to, we have a KE whose value we know, we'll substitute there. We have charge 1, charge 2, that is unknown, divided by what's the distance? 28.0 times 10 to the power -2 square, of course. So since we have this value, we have this and this Q1 as well as Q2 are unknown. That corresponds to have the second equation, that is equation number 2. And I'll be able to solve for Q1 as well as the Q2 simultaneously. And what is the charge on each? So since should have to say what is the charge on each, then we'll have to calculate what is Q1 and what is Q2 simultaneously. Rather, you have that. So pause the video and try that one at your own time. So this is how you should have to understand about the Coulomb's law and some of the questions associated with the concept. Thank you.